Okay, so we know that the Earth's climate is affected by the amount of energy that is absorbed and reflected from the sun. And I'm sure you also know that that climate changes as we go along the Earth in terms of latitude. Now, just a reminder here that latitude are horizontal lines, imaginary horizontal lines on the Earth that we use to measure position from the equator to the poles in both the northern hemisphere and the southern hemisphere. Because the Earth is a sphere, so you can kind of think of this as maybe a protractor, right? If you lay a protractor on the globe here in this diagram, these degrees represent latitude, degrees of latitude. And you know that it's hot at the equator and it's cold at the poles. But why? So the poles are tropical. After we cross these two latitudinal positions, the Tropic of Cancer, the Tropic of Capricorn, those are considered temperate regions, and that's where we live. And then after you cross the Arctic Circle at 66.5 degrees south or 66.5 degrees north, those are considered polar regions, and they're colder. And the poles are at 90 degrees. So why do we have this change as we go from the equator to the poles? Well, it has to do with how spread out the energy from the sun is. When the sun strikes the Earth at the equator, it's striking most directly, and that sun is, well, if you think about these as these beams, and this is a simplified way of thinking about the sun's energy striking the Earth. It's just for diagrammatic purposes here to help you understand. This isn't actually the way it looks, when the sun's energy strikes the Earth, but each one of these beams is supposed to represent an equal amount of energy. So all of these beams have the same amount of energy, even though this one looks like it's a little thinner than the others. So that energy is striking a particular area on the Earth. And as we go up in latitude, either north or south, as we increase in latitude, in other words, move away from the equator, that same amount of energy is being spread over a larger area, because the Earth is a sphere. And by the time we get to the poles, it's spread over a much larger area than it is at the tropics or at the equator. So the idea here is that the reason the equator is tropical and the poles are polar is because the same amount of energy is spread over a much larger area at the poles. So that wherever you are in that area, you're receiving less solar radiation, you're receiving less energy than if you are at any particular place within that area at the equator. Just like the effect of latitude, the effect of the Earth's tilt on its axis as it orbits the sun has an effect on the amount of energy or how directly the sun strikes the Earth, and the amount of energy then that's absorbed at any one position on the Earth. So the idea here is that the Earth has an invisible axis. So obviously there's not really a line running through the middle of the Earth, but the Earth revolves around its axis. It's like a wheel on an axle, and it revolves around its axis, and that axis is tilted in relation to the sun. So it's not straight up and down. And as the Earth orbits the sun, it stays tilted at the same angle all the way around the sun. So that when it's summer in the north, the northern hemisphere is tilted towards the sun. Therefore, the sun's energy strikes the northern hemisphere more directly. So that's the most direct sunlight. That also results in longer days. It results in longer days. And that delivers more energy also, because there's more time for the solar energy to be delivered and build up in the atmosphere and affect climate. As the Earth orbits the Sun, when it gets to this position, that would be autumn in the north, fall, the Sun is striking the Earth in the northern hemisphere less directly. So it's still striking relatively directly, but less directly than it was in the summer. And then as we go into the northern winter, that's when the Sun is striking the northern hemisphere least directly, because the northern hemisphere now is tilted away from the Sun. And we have shorter days, so there's less time for solar energy to be delivered and absorbed, in addition to the fact that it's not striking the Earth as directly, or the northern hemisphere as directly. In the northern spring, then, we find the same situation as in the northern autumn, where it's more direct than it was in the winter, but it's still not as direct as it is in the summer. And then I just went ahead and threw on the information for the southern hemisphere also, which is the opposite. You know, when it's northern summer, it's the southern winter. And when it's the northern winter, it's the southern summer. So that's the effect of the Earth's tilt on its axis as it orbits the Sun. So we've seen how energy is delivered to the Earth, and once that energy is absorbed, it is distributed around on the Earth partially by wind. So what we're looking at here is transport by moving air in the atmosphere, what we call wind. And there's this concept known as prevailing winds, which is the predominant direction the wind comes from. So when we talk about wind direction, we're talking about the direction that the wind is coming from, not the direction that the wind is blowing to. And it's due to uneven heating of the Earth. The prevailing wind directions that we see in this diagram are the result of uneven heating. And so that's what we were just looking at on previous slides, how the equator absorbs more energy and therefore it's hotter in the tropics. And that produces, in part produces the wind direction along with the rotation of the Earth. So you can kind of think of the Earth rotating out from under the air, therefore the air feels like it's moving in the opposite direction of rotation. So the Earth rotates counterclockwise, and therefore the wind, the atmosphere above it, is moving over the Earth's surface from east to west in the equator, along the equator in the tropics. So that's how we end up with the prevailing winds that we see here in the tropics. They are easterlies. Even though they didn't put that on here, you know, they're obviously blowing from east to west. Then as we go across the Tropic of Cancer and Capricorn and get into the temperate regions, we've got westerlies. And that's where we are. If you watch the weather, you know that our weather comes across the United States. Pretty much the weather that they have out west is going to eventually arrive to us. And that's because our prevailing winds are westerlies. It's the same in the southern hemisphere in the temperate regions. And then as we get into across the polar circles, then the winds switch again and become easterlies again. If we look at this diagram, kind of another aspect of the way that the air is circulating in the atmosphere, so the air above the Earth is circulating in these things referred to as convection cells, because they're produced by convection currents, or they are convection currents, which means that the air at the equator is warmer and therefore it rises, and then it circulates around and cools and falls back down to the surface of the Earth, and then blows as wind across the surface of the Earth, and then as it warms, as it approaches the equator here in what they call this Hadley cell, it rises again, and that just continues, and that's a convection current. Now, they name these according to scientists' names and where they are. So these Hadley cells are closest to the equator, and then we've got these Ferrel cells on both sides in the temperate regions. And then we have polar cells. And what's happening here is heat's being handed off from cell to cell to cell that results in generally the transport of heat from the equator to the poles. So the Hadley cells hand off some of their heat to the Ferrel cells, and the Ferrel cells hand off some of their heat to the polar cells, and we end up with the transport of heat from the equator to the poles. We also find that heat is transported around the globe by water. So just like the movement of the air in the atmosphere transports heat, the movement of the water in the hydrosphere transports heat. And so in this diagram we see some of the major ocean currents, and you'll notice that there are warm currents and cold currents. The warm currents are made up of, like the name implies, warm water that is less dense, and it's also less salty. So that makes it less dense. So it's not only warm, it's less salty, and those two combine to make that water less dense. So these warm water currents are running along the surface, whereas the cold water currents are more dense. They're more salty also, so those two combine to make them more dense, and therefore they run deeper. They run basically along the bottom of the oceans. Water is really good at transporting heat around, as it says here, because of its high specific heat capacity, which means water has and we're going to learn this when we study chemistry and aqueous chemistry, which is the chemistry of water. High specific heat simply means that water is really good at absorbing energy and storing that energy, and then that energy is slowly released. And in the case of heat transport around the globe, the water in warm regions, like along the equator, can absorb a lot of heat energy, and then as it flows through currents, it transports that heat energy and then releases that heat energy slowly into regions away from the equator. Now, if we summarize all the ocean currents, we end up with this thing that they call the Great Ocean Conveyor. And as you can see, if you kind of analyze this diagram, the Great Ocean Conveyor conveys heat energy northward on the planet, on the Earth. So that makes the north warmer than it would be without this transport of heat by the Great Ocean Conveyor, or by the currents in the oceans. So if you think to yourself, what would happen if this Great Ocean Conveyor were to stop? And that is something that some climate models have predicted, that as climate change continues and the Earth gets warmer, it's going to affect ocean currents, and it may affect ocean currents so that the Great Ocean Conveyor stops conveying heat the way it is now, and that may result in less energy being delivered to the northern hemisphere. And actually, even though climate change is generally global warming, that doesn't mean that every place on the planet is going to end up warmer than it is now. So, for example, if we mess up this system that's conveying heat from the equator northward, it may throw the planet into another ice age, which is actually the basis for the science fiction movie Day After Tomorrow. If you've ever seen that movie, that's the basis for that movie, that climate change has shut down the Great Ocean Conveyor. Warm water is no longer being delivered to the northern hemisphere, and that throws the Earth instantly into an ice age, according to that movie. Now, of course, they exaggerate the effects and how quickly it would happen, but that's the idea and the importance of the Great Ocean Conveyor and heat being transported around the Earth by water.